We now take problem number 85 of your textbook. This problem, it's arithmetic is very small, but there is a lot of things that one need to understand. I mean, as I said, it is very important to understand what is described in the problem. It says a solid sphere, mind it, it's solid, that means moment of inertia is 2 by 5 mr square, is set into motion on a horizontal surface with a linear speed v in the forward direction and angular speed v by r in the anti-clockwise direction as shown in the figure. This figure is given in your textbook. Now look what is happening. This figure says that angular rotation is anti-clockwise, but it is released on the ground with a forward velocity of a v. These two are contradictory to each other because it is very clear that if you have a ground like this, and if you have a sphere like this rotating in anti-clockwise direction, the sphere will shift gradually backward. That means there will be a backward motion of its center of mass. But then what the question or the paper setter is trying to say, it is like as I gave you an example, it is like a spin bowler throwing a ball. He throws the ball in forward direction, but gives it a spin in backward direction. And then it touches the ground. That is exactly what is happening here. So, have to be pretty cautious in solving this problem. Here, we start this way, that the linear motion and angular motion are in two opposite direction, or I think that is not a correct statement. We should say linear motion v or linear velocity v. I write it this way. We write it here. Linear velocity v acts to produce an anti-clockwise. Now, it will produce a clockwise angular motion. This is the first statement. But the ball has an initial anti-clockwise angular motion. Anti-clockwise angular motion. So actually what will happen to the ball? After the ball has reached to a certain point, it is said that when it stops rotating, it means the angular motion created by the linear forward velocity is more than its initial angular motion. That means at certain point here, coming to a certain point here, it will stop. Its angular motion will stop. It will only have a linear motion. This is how you must understand the problem. This angular motion here stopped because here this linear velocity v creates a angular momentum in this direction, which is equal to, and measurement of that momentum is mv multiplied by r. And mbr is more than or larger than the initial angular momentum, which is already given in the body. So here it stops, rotation stops. Here I say rotation stops. And let us say at this moment its velocity is v naught, right? And the paper setter wants us to find out this velocity v naught. Say its linear velocity when the pulling stop is equal to v naught. We have to find out the value of v naught. It may not be difficult to find out. Initially, it has two angular momentums. One momentum in the clockwise direction, initial angular momentum. What is the initial angular momentum? Real angular momentum is equal to angular momentum by the linear velocity v is higher, and it is angular momentum is mvr, and minus it has got an angular momentum of I omega due to the angular velocity already imparted to this. Mind it, MVR produces a clockwise angular momentum, or due to clockwise motion, I omega is anti-clockwise motion. That is why there is a subtraction is equal to MVR minus I. I is 2 by 5 mr square multiplied by VR. I omega. Omega is equal to VR. Sorry, omega is equal to V by R. 2 by 5 mr square multiplied by V by R. Since omega equal to V by R. This is equal to, here this R and R square gets cancelled. We have only one R left. So MBR minus 2 by 5 MBR is equal to 3 by 5 MBR. So its initial angular momentum, net angular momentum is 3 by 5 angular momentum. And say this is condition 1. And this is condition 2. So we write in the second condition, in condition 2, when rolling stops, then its angular momentum is for linear velocity v0 only. is only for its linear velocity v0, which is equal to m v0 r. Now, this 3 by 5 mvr and mv0r has to be equal to satisfy the law of conservation of linear momentum. So we write to satisfy to satisfy the law of conservation of angular momentum, satisfy the law 3 by mvr, mv0 r will be equal to 3 by 5 mvr. So here this r and r gets cancelled, n and m gets cancelled. What we are left with v0 equal to 3 by 5 v. So v0 is equal to 3 by 5 v. This is they wanted us to find out. What is the linear velocity when the rotation stops? Now let us look back the sphere once again. When it stops, this V0 still creates a torque on this body, which is equal to mv0r in this direction. So now what will happen? This body sphere will start going forward with a rotation in clockwise direction. With the rotation in clockwise, say this velocity is then v1. If this velocity is v1, what is the angular momentum? So what is the angular momentum created by v1 is mv1 multiplied by r. And also it has got an angular velocity omega. Also it has got an angular velocity omega, which omega is only due to v1, which omega is actually due to then v1 by r. I think I could explain this properly. Here the rotation in situation 2, the rotation has stopped. In situation 3, and since v0 is not 0, that means the ball continues to travel in the forward direction. And if it continues to travel in the forward direction, this v0 creates a torque, and that torque creates an angular motion omega, and the torque creates a linear velocity v1 of its center of mass. And now since it's a pure rolling, this is pure rolling, now it is pure rolling, and pure rolling, the relation of omega equal to v1 r will hold good. With that, what is the net angular momentum in condition 3? The net angular momentum when rotation, this rotation is now clockwise rotation. When rotation starts, net angular momentum when rotation starts is equal to then I omega let us do one thing. Let's call it omega 1 because at the very beginning there was one omega in counterclockwise direction or anti-clockwise direction. Now this is a clockwise linear velocity, angular velocity. Let's call it omega 1. I omega 1 plus its linear velocity v1. So m v1 r. Let us write here, assume angular velocity is equal to omega 1 and linear velocity is equal to v1. In fact, the paper setter wanted us to find out the value of v1. So this is the velocity at that time, which is equal to angular momentum at that time, which is equal to I is 2 by 5 mr square multiplied by omega 1 is equal to v1 by r. Omega 1 is v1 r, v1 by r. This is m v1 r. This is equal to, from here it is, we get it is 2 by 5 m v1 r. So it is 2 by 5 m v1 r plus another m v1 r. M v1 r is equal to 7 by 5 m v1. M v1 r. This is the angular momentum now in the position 3. But angular momentum cannot be generated. You know, angular momentum or linear momentum, it can be only transferred from one to other. It is only transferred from one to other. What was the basic initial angular momentum? Was 3 by 5 mvr, and basic angular momentum is 3 by 5 mvr. So this final angular momentum in position 3, 7 by 5 mv1r has to be equal to 3 by 5 mvr, right? So once again, to conserve the to conserve momentum or angular momentum, conserve angular momentum, this 7 by 5 m v1r has to be equal to the initial angular momentum 3 by 5 m vr. Here m and m gets cancelled, r and r gets cancelled, 5 and 5 gets cancelled. So what we are left with, v1 is equal to 3v by 7. So v1 is equal to 3 by 7 v. This is so. Now look at the problem once again. It started with forward velocity v. Somebody has given it a velocity, like, as I said, like a spin bowler. When you gives a ball, the ball has a forward velocity. Also, it maybe have a reverse spin. It has got a forward velocity v at the beginning, this ball here, and it has got a reverse spin omega, which is equal to v by f. Then these two angular momentum, they oppose each other. At some point of time, this initial reverse spin stops, and at that time, at that moment, its linear velocity of the center of mass is v0, which is equal to 3 by 5 v. And it continues to move but it continues to move over a surface. If this ball would have continued to move in thin air, then it would continue to move only. There was no more chance of rolling. But it is continuing. It is now continuing. It is moving on a surface, on a ground, say. So this velocity v0 get a clockwise torque on the ball, and the ball will eventually start rolling once again. And finally, say its linear velocity becomes v1 and angular velocity omega 1. This final velocity v1 is equal to 3 by 7 v, where v was the original linear velocity with which the ball was thrown. So this is it. Then we go to now next question.